So for what you need to know about probabilistic models for the final, we touched on some of this, I think, in set 6, but the main probabilistic model that you need to know is just naive Bayes. So the key assumption here is that when you have a set of features and you're trying to predict some other variable, you can assume conditional independence between the features so long as you're conditioned on the, for example, label you are trying to classify. So formally, this would just be let's say xi conditioned on xj where j is not equal to I, and your class, so let's say C, is going to be equal to probability of xi given C. Effectively, conditioning on the other features won't give you more information about a feature so long as you know the class. So you all had to work through a less clean version of this as the full model, where this assumption no longer held, and we showed that the number of parameters was that one needed to store to do so was exponentially large. So instead, this is why we have the naive Bayes assumption. To actually perform inference, what you do is you simply apply Bayes' law. When you apply inference, what you're trying to do is predict the class given your features. So you can decompose this into just the marginalized probability of the class, the probability of the features in the first place, and then the probability of observing a feature given the class. And since you have this naive Bayes assumption, you can cleanly decompose it into just a series of products. And your products terms should just be the probability of predicting a given feature on the class. And importantly, unlike the full model, we do not need a condition on other features. And instead, we can just only condition on the class, which also means that the number of terms that we need to store in order to compute the product now becomes linear with respect to the number of features we have. And so we have that this value is proportional to the probability that we need to perform inference. Note that that's a scaling factor, so that's going to be 1 over p of x, but you can disregard that because you can assume that you don't really care about the probability of observing x for classification since the data point is already there. So once you have this, once you have the intuition for obtaining the inference, which is something you'll need to know how to do by hand for the final, you also should have a good idea about the different ways of performing estimation or different ways of performing estimation over possible values of CK. So once you have this probability, what you'll need to do is note that you are simply trying to take the maximum of this value. You're trying to find the most likely class given on your data. Note that since we scale by the prior probability of observing a class, this corresponds to the maximum a posterior prediction. But if we did not have this term, then you could view this as just the likelihood of obtaining the data, in which case you would have the maximum likelihood. And yes, the maximum likelihood estimation is what you'll get if you take the argmax over this probability. So if you take the argmax here, it's going to be the maximum posterior. Otherwise, it's going to be the maximum likelihood estimator. And you'll observe that when the prior is uniform, then they're equivalent. So this just relates again to the distinction between Bayesian and Bayesian detection and just Bayesian estimation and just normal frequentist estimation. Yeah, so I think that's all I need to know for probabilistic models, at least.
Although we haven't seen the final, just so that this review can be fair. So again, caveat that's going to be on our lecture notes. Make sure you review the slides in general and use this as like a supplement or a way to like figure out what you don't know. All right, Marcus.
Great job, Eric. This is going to be a hard act to follow. You might not erase this?
Not at all. We have it recorded. Yes. Marcus, that's unless if you're not drawing anything in the cell, that's fine.
Yeah.
Yeah, it's just feel free to like use up any part of the board. Like we have the entire thing.
Okay.
That's small. That's too small.
Too small.
Like, okay. Let me help you out here. Let's see. Make things as large as
Ah. Alright, so that average is just too small.
I really hope it's not backwards. The video. No, it's not. We're good. Oh, and guys, if you ever have any questions, just like comment in the chat, and then we can answer. No problemo. Yeah, that's super clear. That's really great.
Thanks, Alex. I appreciate and understand your critique. Hi. So this is a this is a general review of some convolutional neural networks. So in general, we have this concept where we have this filter, and we pass it over an image like so, and basically from that, we use this as input to our convolution into our neural network. And then what you can do is you can have convolutional neural networks. You can pass them into other convolutions, and then if you do that without padding, what's going to happen is that your image is going to get smaller and smaller. And then what this means is that you can actually make it such that like you go from a big image representation, and then as you pass filters over it in your convolutional neural network that are learned, then you get more and more abstractions. And so then like it's been shown that you can like have like different like level features. So like in the first pass over, you like look at small things, and then like as you go more and more, and like the image gets smaller and smaller, and you go through more layers and layers, you go through bigger and bigger concepts. And so it's really typical in convolutional neural networks to have your filter be of size 3 by 3, and then just do that again and again. And this can be also really interesting because this is super useful like in segmentation, for instance, that you can have like it's bigger. Where you can like have this be like your input size of the image, and then go through some convolutions, and then you'll eventually get to hear like some latent representation, and then you can also just build up back from that using fully connected or deconvolutional to do whatever you want. But yeah, basically with convolutional neural networks, you pass a filter over, and these are learned, so then you can abstract out higher concepts of the image. And then these are just some example filters that are commonly used for just like image processing in general, and just give you a general intuition of like what kinds of things your network can be doing. So we have the averaging filter, and so what this does is it just blurs the image. And like for this, you just see that all the values are 1/9, because whatever the values are around you, you just add them up and then you average to blur it. Sharpen does the exact opposite. Whatever values are around you, you try to negate those, and you just concentrate on the value in the center. And then this example is a horizontal edge filter, where basically you just look at the difference between like the line of pixels above you and the line of pixels below you, and then these different values should give you like where there are lines that are horizontal in the image, because if you have like a big difference between like the top part and the bottom part, then that'll indicate like a horizontal line, kind of like and then just nothing. Yeah, let's see. What else is there on? Oh, yeah, a convolution in general is when you take the dot product of the filter and the image. So you just add up every single cell in your convolution with what's in the image as you pass it over. And that's how you get it. So yeah. So this is really good for image data, since it's it takes into account locality of data. Is it? Oh, always 2D over 3D comes from neural networks. That is the general rule. I think we.
Did you want to cover there's other parts of section 4? So, oh no, that's section. Oh, that's my stuff. Okay, yeah, I'm good. I can start.
Thanks everybody. Like and subscribe.
Okay, so hi everyone. My name is Alex. I'm gonna introduce myself. So we're gonna talk about regularization techniques. But before we do that, just one last note. Thank you, Marcus, for doing a great job on this. Most of our dimensionality reduction is going to be from things like pooling. So while the lack of padding, let's say it might take off 2 or 3 pixels off the edge of your image. For an image of, let's say, 200 by 200, that's not going to be too much an effect. What is going to be quite an effect is pooling, which, basically is when we do something like we take the maximum, let's say, we're doing max pooling of this portion of the matrix, and then we kind of reduce, let's say, our matrix down to these like maximums. So let's say we have one here, 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 here. That turns this 15 by 15, into a 5 by 5. So just wanted to clarify that. Let's say, if we had a filter that looked like that, like a 3 by 3 with a stride of 3. There's also another option. You can take the average pool. You can also take the max pool. So now let's talk about different types of regularization. So for some techniques, such as the main one being neural networks, we want to add some sort of penalty to having big weights. And in general, this is so that we can keep the model complexity small. And the reason we want to do such a thing is because if our model complexity is too large, again, we have this bias variance trade-off where we might find a solution that fits better to our training data, but actually is less generalizable and makes much more like wild assumptions about the data. So there are 2 that we've talked about. So one being the L1 lasso. I'm just going to write it out for you here. So what I'm writing out specifically is the modified loss function and then I'll just write out the L2 ridge for you. Okay. And so I want to emphasize the main difference here is the regularization term, where here we're trying to reduce the absolute value of our weights, whereas here we're only trying to reduce the L2 norm. So as you know from class, this makes a big difference in how your weights get treated, right? And so we saw that with L1, as we increased lambda, we saw our rates generally like go down to 0 in like kind of like this manner. But for L2, they don't seem to do that, such a thing. They kind of asymptote to 0. Okay, and so I just want to provide some intuition of why that is. So the primary thing is that so let's say if we actually look at the optimization surface of our landscape, so sorry, what the heck does that mean, right? So let's say we had two weights only, weight 1 and weight 2. And I'm gonna draw a contour plot of the loss. So you can imagine, let's say, here's where the minimum loss is, here. And then as the contour gets bigger, the loss gets greater, okay? When we are using our L1 norm, what we're doing is basically putting a constraint on this optimization space that we're allowed to traverse. So let's say, this is the best part of the optimization space. It's in the middle here. What the L1 does is it creates this kind of diamond diamond constraint. And so basically what this leads to is that you have one weight that usually is going to dominate over the other. And the optimal strategy, like if you were just looking at this as an optimization problem, would just be take the maximum of W1, because you're making a trade-off between how big W1 can be and how big W2 can be. And okay, while this example is not the clearest, let's see. Yeah, I kind of drew one that's like very ambiguous. But if it was more, something like this, yeah, then it's kind of clear that that's the maximum in our strategy. So on the other hand, with L2, like if we only have two weights, the constraint we're placing on our weights is circular. So let's say now our L2 norm looks maybe something like this. And you can imagine that the circle extends. And so we can see here our optimal is actually taking a mix of W1 and W2 because that gets us closest to the optimization target. And so that's just a basic reason of why this happens. And so you see W2 might give, ridge regression might give us actually a better fit and a closer, give us closer range to where we want to be. But for the purposes of feature selection, when we're trying to look at features that, sometimes there's just, they're random and they're actually not correlated to our objective, but they seem that way, the lasso regression is a great way to get rid of that. And you can use that for model compression too, so reducing the number of weights or the input size. Those are all great things to do. Are there any questions? No, nothing from the chat? How surprising. All right, so let's go into just two more things that are commonly used for regularization. Okay. So another approach that was actually created right in my hometown in Toronto is Dropout, created by Jeffrey Hinton of University of Toronto. Amazing professor, amazing place. So this method was developed to address overfitting in neural networks. And so I'm gonna draw just a super simple neural network right here. All right, so one problem that we've seen in neural networks, especially if we try to make them too large and scale them up, is that they have stability issues. So you can imagine, let's say we're trying to analyze some sort of housing data, okay? And then we have some inputs here, which is descriptions of the neighborhood, and we want to figure out what the cost of the house is going to be. So you can imagine, I have some these hidden nodes represent something like the safety of the neighborhood, and they might represent like other latent factors, right? So if we make our network too large, I guess one of the problems is we can be overly dependent on one node for like that kind of information. If you kind of imagine these nodes like carrying information forward through the network. And so in the same way, like let's say you have a campus of health advocates, right? You don't want just one health advocate who knows everything and can do everything, because like what if they come down with coronavirus, right? You want a network that have some redundancy to it. And so that's why we can use Dropout to increase the amount of, let's say, redundancy in the network, and that helps to like increase the stability. And so how this works is during training, we'll randomly take a subset of the nodes and use those to calculate the actual like input to let's say the output layer. And so in training, we can have one batch where let's say on batch 1, then this node is out, and on batch 2, this node is out, etc., etc. And we can do this for, let's say we want over 10% of the nodes, just randomly like throw out 10% of them every batch. And by doing that, we can really improve like the scaling of our network. And you might have like discovered this when you're doing set 4, where you're tasked with making your own neural network. And the last thing is quite simple, is we can just add random noise to our input data. Sorry, I take that back. We're not adding random noise to our input data. You can think of Dropout as one technique to add noise to your hidden data. Another approach is adding random noise to our hidden nodes. And so that can achieve kind of a similar thing where we want to make sure that we're not over dependent on this node, so if we add some noise to it, some randomness that can simulate the distribution of like our inputs as kind of being a distribution, then we can have the other nodes configure themselves to account for that. All right, and now I want to welcome my colleague, Eric Zhao.
Alrighty, so matrix factorization. I guess I don't really need the white. Yeah, I'll use the whiteboard. So I won't go into the specific learning techniques or the formulas because those are all in the slides already. So I'll just give some quick intuition. So at a higher level, we covered various forms of dimensionality reduction in class. So you could probably consider clustering as a form. The first clustering method we talked about was where you have centers. So you try to cluster using the center using an E&M style algorithm. So if you have a set of points, let's say you're trying to find 2 centers, you would just randomly place them. You would update assignments of the data points to the centers based off of distance. So that's 1. That's the maximization step. So you assign 1 here, 2 here. But you need to alternate. So along with updating the membership data points, you need to update to the position of the centers to be at the middle, or reduce the L2 distance to the rest of nodes in its reduce the rest of the nodes. So this is called k-means, and normally you could just use an L2 loss because this will more strongly penalize different distances to the nearest. So x minus ck. Yeah. But yeah, so that's the most basic version. You could apply a hierarchy to this and it'd be agglomerative clustering, and I think there's like Rashaal's algorithm for that, but yeah, k-means is the most basic version. Outside of that, we have methods that are called matrix factorization methods, where we instead try to cluster by reducing our problem down to a lower dimensional subspace, so low rank approximations. When you have, so let's go through the most general form first. So that's the singular value decomposition. That's just a decomposition of a matrix, let's say x into u sigma vt, where you have that u and v are orthogonal to each other, and sigma is just a diagonal matrix. This is also like the orthogonal decomposition, and PCA is like how you get it. And in the case of a symmetric matrix, so if x is symmetric, what you'll have is that u and v become identical and will correspond to the eigenvectors, and the values in the diagonal will correspond to the eigenvalues. And this, for example, for PCA, principal component analysis, the decomposition is unique under permutation. Principal component analysis. I don't remember what the proper notation is, but that should be fine. Yeah, so that's because in this case, the eigenvectors correspond with the singular vectors, and because the left and right singular vectors and left and right singular values coincide, so everything is good there. In the case that the more general case, that's just called singular value decomposition. In this case, the u corresponds to the left singular values, the v corresponds to the right singular values, the diagonal of the diagonal matrix corresponds to the singular values. And both principal component analysis and singular value decomposition can be viewed as projecting to a lower dimensional subspace, applying some linear transformation, and then projecting back up to a higher level subspace, projecting to some different, back to either your original space or some other space. Yes. So common applications I think we covered in class were principal component analysis, yeah. Yeah, okay, sorry, I should clarify. There we go. Alright. Yeah. So different ways of solving it. You could use just try to compute it explicitly, or you could do gradient descent. All of those are fine. And application-wise, I think the main application covered was using it to find eigenfaces, so that's pretty exciting. Alright, so in the case that you don't actually want to do this, you could also just decompose it into two matrices. So you could decompose x into a u and then a pt. Yeah, I think that's proper notation. And I guess a common way of solving this is just doing alternating least squares. So you fix one of these, you fix either u or p, you optimize the other variable to get as close to x as possible, let's say over, I think a L, or I guess some norm loss, some norm difference, yeah. And then once you fix a variable, then since this is just matrix multiplication, then it reduces down to linear regression, which you can usually do pretty quickly, either by taking pseudo inverse or if it's large enough, just doing gradient descent. And if you want, you can also expand this to like tensor factorization, where these are effectively higher level matrices, but I don't think we covered that in class, so that should be fine. So one modification you can make here is that you can impose a constraint that all elements of U and P are non-negative. So of course, since you're applying that constraint, the expressiveness of this decomposition is going to be reduced. So you might need to compensate to get the same performance by increasing the dimensionality of U and P. But the good part is that if you impose a constraint that the items are non-negative, then the results become more interpretable. There's less, I think there's less redundancy in there's less redundancy in the representation, because if there is a redundancy, you don't have negative elements to cancel it out. The form name is non-negative matrix factorization. Where, you know, Uij is greater than 0, Pij is greater than or equal to 0. Yes. Okay. And then and another application of matrix factorization that we address is collaborative filtering. So I think this is covered in CS 156B if you're interested. But the idea is that, let's say you have n users, n movies, and you want to figure out for a user what other movies to recommend. In this case, your feature space for a user are just the movies that you know they like, or are just the movies that they have already ranked. And when you are trying to find their probability of liking a movie that they have not ranked yet, you can use that information by taking the matrix X, which contains users versus movies preferences, and you try to find a decomposition, except you don't apply the loss to values of the matrix X that are missing. So those are user movie pairs that we don't have information on and that we're trying to predict. Ideally, the matrix factorization should give us a prediction of how well somebody will like the movie. But yes, so yeah. And intuitively in that situation, you can view one of the matrices as having the latent representations for the movies and the other matrix representing a user's features, which effectively turn into a linear weighting of over the latent space. So yeah, I think that's it for matrix factorization.
Thanks, Eric, for that enlightening presentation. So I'm going to cover just briefly overfitting and what we can do to protect ourselves against it. I think there's a couple ways. Broadly, they fall under the branch of regularization that I talked about previously, where we want to grid search, let's say, our parameters, like our lambda, for example, to find the parameter that gives us the best validation error. So you can also do this directly. Okay, so you can optimize validation error on regularization parameters. But something that might be even simpler and this definitely came in handy during the Kaggle competition, was just early stopping. So you monitor the loss that happens on your validation error between every epoch, and you stop after it hits a maximum or after it stops improving. And what that would look like is, this is our loss curve, and this is our training loss. Let's say this is your validation loss. You basically cut the training here, and then you use this the model that you saved here to do your inference. But now I actually want to go into a bigger topic, which is tree methods. And this will be the final topic of this review session, barring, a barrage of questions. So we learned about tree methods as a pretty effective way to actually analyze, or to model our data if it follows nonlinear patterns. And even if it does follow linear patterns, tree methods give us a pretty robust framework to make really accurate models. And so I think the basics look something like this. So let's start off with the most basic tree model, which is a decision tree. One example of a decision tree could look something like this. So let's say we have some data points that we're trying to classify. Let's say, sorry if those are too small. Yeah, actually they're quite small, so I'm just gonna draw a little fewer but larger circles. Add a little bit of noise into this model. And this could be any classification problem. Let's say we're trying to classify whether someone skis or snowboards, right? So let's say red is snowboard. And on this axis you could have how west they are. And this axis you could have how young they are. Alright? Simple model. Okay, so we could have a decision tree basically being like, hey, let's make two very basic boundaries. If you're very young and you live very close to the west coast, let's see, what would be a good threshold? Actually, that wasn't a very good first threshold. Yeah, let's do this and this. We basically say, okay, everything in this region we classify as skiing, everything in this region we classify as snowboarding. And these are people, by the way, despite them not looking like people. So this decision rule would be at the top like, oh hey, are you like west of Colorado? And then, let's say, we only have one child in this case, under, let's say 30 years old. And if you answer yes to both, then you snowboard. And if you answer no to either of them, then you ski, which, is fine too. I like skiing. I like snowboarding better. Okay, and so how do we actually build these kind of trees? Well, as you might remember from lecture, we basically start with a primary node of which We don't know what the decision boundary is going to be. And we look at what is the split, so what is the line I can draw that separates the points that would actually decrease my loss by the most. So we can quantify the loss with something like entropy. So I'm not going to go into the equation, but you can see it in the lecture notes. Let's say this is this is entropy, and this is PS. Okay, so what does that mean? Basically, if let's say we cut the cells into two, right? So now we have two blocks. We look at the entropy of both those blocks, and we want to minimize it. So in this case, we minimize it by either having the blocks only have skiers or only have snowboarders. And if they have like an even mix of the two, that's actually really bad. And so we can basically just go over every single different split that we can do or sample from the total number of splits that are available, and basically find the one that works the best. So as you can imagine, we can split this data set infinitely, right? So we can add a line here, we can add a line here, here, and here. So, but there might be a problem with that we kind of discussed previously, which is this could really overfit our data set, right? Because now, even though this was an outlier, we're classifying like these regions as snowboarders. And so basically, most of decision trees is figuring out how can we reduce the variance and possibly also the bias of these trees and turn them into very effective learners. So for a strategy like this, let's say if we're only looking at decision trees, like a single decision tree, the way we can prevent ourselves from going to overfit is by setting a limit. So for example, there could be the minimum number of examples in the leaf node. So we could say, oh, you might have to have at least 3, and that would prevent these like small pods from forming. You could have the maximum number of nodes themselves, so set it to 2. Or you could have a minimum impurity reduction. If you don't reduce the impurity by a certain amount, then don't even consider that split. So that works for a single decision tree, but that doesn't give us generally a very strong model. And so we can use a few other strategies that really take it to the next level. So one such strategy is bagging. So bagging stands for bootstrap aggregation, and generally this approach is used to take complex, low bias, but high variance models, like a decision tree right here, and reduce the variance. And by doing this, we can reduce our test loss. So essentially how this works is we use a technique called bootstrap, which allows us to get almost like new data sets from our existing data set. And we do this by resampling it. Just to clarify what that means, let's say I had a data set with points 1, 2, 3, 4, 5. 5 data points. If I wanted to do bootstrap aggregation, I would sample with replacement from this data set to make more equal sized data sets. So let's say I sample a new data set and it's like 1, 2, 2, 4, 4. Or I maybe get 2, 3, 3, 5, or 4, 5. Something, it could really depend, but you can kind of see we just basically keep recycling this data set to create new ones. And so you might think to yourself, well, that doesn't really make sense. Like, why would that give us better data? In fact, aren't we like misrepresenting the quantities of single data points, right, by resampling them? And so through a bunch of complex statistical analysis, people have found that actually no, that's not the case. In fact, if you have an estimate, let's say you want to estimate the mean of a data set, and if you use bootstrap sampling and you average the measurements of each data set that you generate, you can get asymptotically consistent estimates of the true population distribution. And this is assuming that your training data is sourced from the true population distribution. Otherwise, there's no hope. But this can help cure the particularities of having not a big enough data set or of sampling itself. So then what do we do with this information? Well, now we can take this and make a little tree or a big tree, depending on how you like your trees, for each data set. And then all we do at the end, very simple, we just take the average. And so that will give us a reduced variance estimate, basically for free. So that's pretty awesome. Can we take this even further? Yeah, it turns out we actually can. So let's say now we can go to another approach called random forests. So the innovation of random forests is that, again, we're going to do this bootstrap aggregation, but we're also going to do some sampling of the features that we consider on every node. So how this works. So let's say right now I'm at the root node, right? And I'm trying to figure out which split I'm going to do. So generally we would search through all the splits here and here on both dimensions, but we could choose to only look for splits of young and how young they are. And while that might not have been the best split in our data set over here, the best split, the first one to do was whether you're West or not, we could, right, easily just draw a line, let's say here, that does the job, right? And so at every node, we're actually just going to sample which features we're going to consider splitting on. All right, so it's very simple. We can kind of call it feature bagging. It's a similar thing. And so by doing this, we get a forest of trees. We aggregate the result by averaging them. And so this actually works really well, and it works even better than just normal bagging. And the reason why is because, let's say we generated these couple of trees. We might get a lot of trees that are actually extremely similar because we resample the data, but every time we're going to draw, let's say this line, pretty much the same location, and the second split line, it's pretty much the same location if we have a big enough data set. And we don't necessarily want that because that means all our predictors are very correlated, and that actually prevents us from reducing the variance by too much because we have kind of less, we actually do less learning overall by having less diverse models, and this prevents good generalization. And so by doing this, we can kind of decorrelate some of the trees and increase the goodness of our models. All right, and so that was bagging, and primarily the purpose of that is to reduce the variance of low bias, high variance models, so complex models. However, let's say we wanted to do the opposite. I'll erase this. So now let's say we wanted to take very weak learners, so learners that only barely learn something about the data set. And it could be a very shallow tree. It could be one node, it could be 2 nodes. Let's say it's just a depth of 2, right? Very standard. So what we can do what we want to do with these kind of models is, let's say we have a bunch of them. We actually want to have their bias be reduced. So they are high bias but low variance models. All right, and when we say reduce bias, we basically mean let's make them accurate, let's make them fit the data better, right? And so one primary example is for regression is called gradient boosting. And so you can imagine what we're doing is basically taking our input data, let's say it's X and Y, okay, and they're some numbers, blah, blah, blah. Great. So the basic process of how this works is we're going to get a very weak learner to learn an initial estimate for y. Let's say we're gonna call that like y hat 1. So there's gonna be a lot of error, right? And we can represent that error with a new column, y minus y hat 1. Right? So now we have blah blah blah, we have a new data set. The step is very simple. Now all we do is just try to fit another weak learner on the residuals or the error of the previous model. And for the CS156B competition, this will turn out to be a useful technique to further increase your accuracy. So now we have y2 hat, right, which is an estimate of y1 of the error of, let's say, of the first model, okay? And now all we do is create a new training data set that is this, etc. So you can see this technique is, the logic of it is pretty simple, and we just keep iterating this process. So this works great, called gradient boosting, and you can see it employed in some of the most successful models like XGBoost and GBMs, gradient boosting machines, or extreme gradient boosting. There's also a classification version that is pretty complex, so I'm not going to go into it now. I'll just broadly describe it, but if you look at lecture 6, it will fully kind of detail what's going on there. Essentially, and before I get into that, so our final prediction from this model is going to be basically, again, like I believe a summation of all our predictions. So we're like, okay, we have our initial estimate, let's account for the error, let's account for the error of that accounting, and so forth. And so you just aggregate those observations to create your final regression prediction. So with AdaBoost, we're taking a slightly different approach, where instead of trying to predict the error per se within every new tree, all we're doing is reweighting the samples so that when we train a new tree, it'll have different priorities of where it wants to learn. And basically by doing that, we can again simulate this process of trying to get the portions of the data set that we get wrong the most to be corrected by the next tree. All right, and so the last thing that we want to cover is something called ensemble prediction. And so this is a pretty interesting technique that actually achieves maybe even the highest score of all these methods. And again, very simple. Let's say we take our data set and we set 30% of it to be validation and 70% to be trained. And we don't have a test set, let's say in this case, but we could employ one if we wanted to estimate the test error. So now from this trained data set, let's train 5,000 different trees. So we have 5,000 trees, and maybe they could be different in somehow. You could beg. Actually, I would recommend probably do some begging. Now that we have all these trees, okay, how can we combine them optimally so that we have the maximum, the minimum test error, or the maximum test accuracy? So we can simulate our test set with our validation, and that's the basic logic behind this. Let's just pretend validation is a really good approximation for our test error, and basically combine these trees in a way that minimizes the error in validation. So the specific way they do this is very interesting. So let's say you have your set of trees. I'm just gonna draw them as like no arrays. And then, so this is, say your set, what do I call it here? H of like hypotheses. And then here's your set G. So G is the set of trees that we actually want. So it's, again, this is an iterative process. So let's say let's say for the first step, we just want to choose a tree that has the minimum validation error. So then let's say it's this one. So like we move it over. Now we look at what tree, when combined with the existing ones in G. So let's say if we had to take a tree, put it into G, and then we took the average of the predictions of the trees in G. Which one of those trees in H, when put into G, would minimize the validation error? So that was like a very roundabout way of saying, let's just make G as good as possible. So let's say the next one that we want is this, right? Let's say this model actually is very good for accounting for some of the biases and errors in this model, and so together they work super well. And we put into G. So now we have an even better model, which is the aggregate of the predictions in G. And we keep doing this until we either plateau or we stop like reducing the loss. Now, the aggregate predictors that you get from your trees in set G are going to be a really good model for your underlying test distribution. And so some of the advantages of this technique is that, again, we don't have to worry about bias variance. We can just directly optimize our metric. And some of the disadvantages is that we have, we pretty much completely rely on this validation set being good. And so we want to make it reasonably large. And we also want, that also just means that we're going to have less trained data. All right, so with that being said, are there any questions? And I'm just going to wait a couple seconds because I know that Twitch has quite a delay on the number of questions. Well, I'm just getting a few more seconds, no worries. And I just want to say, in these trying times, I think you guys are going to do great on your CS 155 final. Don't worry about coronavirus. If you just focus on your love of machine learning, yes. Sorry. Then I think you can get very far in life. I remember when I first learned about machine learning. It was a beautiful moment. And there's been some lows, that's for sure. There's been some highs. But overall, I think it's been a really great trajectory. Super useful topic and in the industry of the world. And I think we're gonna, machine learning is gonna rule the world into the future. So, keep it up, guys. You're doing great. The averages on the sets have been quite high. And I think that's a testament to the undying spirit of the Caltech student. All right, and I don't think there's no questions, so thank you.
So is that one high a month?
No comment.
Dude, do you think